All right. Good afternoon. Any questions before we start? So we start with force analysis. So let's continue that. We are just reviewing what you have covered in dynamics and statics. So you are familiar with finding the center of gravity for a rigid body. So how can we find the center of gravity? We are gonna set the first moment of mass equals to 0 to find center of gravity for a rigid body. So for example, you set the integration of x dm. dm is the mass element. Set it equals to 0. Set y dm. Set equals to 0. And set z dm. Set it equals to 0. By doing that, you will find x for center of gravity, y for center of gravity, and z for center of gravity. You find the location of center of gravity. In this course, we are not looking for finding the x, y, and z. I'm just reviewing how can we find the x, y, and z of center of gravity. So this is the first moment because coordinates times the mass element. If we have second moment of mass. So for example, Ix is gonna be y squared plus z squared em. This is gonna be the Ix. Sometimes they say Ixx to reflect the second moment. Iy for second moment about y-axis, it's going to be x squared plus z squared em, and izz, it's going to be ix integration of x squared plus y squared times dm. This is how we can find ixx, iyy, and izz for second moment of inertia with respect to x-axis, y-axis, and z-axis. We are not gonna go through this I'm not asking you to find the second moment of inertia for any rigid body, but we need to review that because we are gonna use the mass moment of inertia. For some the standard form of the mass, I have the I in this table. So if you have single point of the mass point, just concentrated mass, which is rotating about the center with the distance of r, it's rotating. This point mass is rotating about this, and the distance is r. I for this is going to be m, whatever is the mass, times r squared. If you have a bar, like a 4-bar mechanism, which is rotating about this axis, at center of gravity, the I with respect to this center of gravity is going to be 1/12 m L squared. L is the length of the bar. What else? If you have this shell, cylindrical shell, it's going to be I equals to m r squared. M is going to be the mass of the shell, r is the radius. And if you have a solid cylinder, I with respect to z is given, I with respect to x-axis and y-axis can be calculated by this. And if you have a disc, if this is a disc, just a plate, the I with respect to this axis and the other two axes are given. So if you look at these two bars, this is one bar and this is another bar. Here the mass moment of inertia with respect to this axis is going to be 1 over 12 ml squared. So I with respect to center of gravity is going to be 1 over 12 ml squared. And L is the length of bar. So if I change the axis from center of gravity, it's passing through the center of gravity to this point. So I with respect to z, if this is the z-axis. There is a theorem which says if we have parallel axis, as you see, this axis is parallel to this, and this is gonna be the axis passing through the center of gravity. So I with respect to the new axis is gonna be the I with respect to center of gravity plus mass, whatever is the mass of the rigid body, times d squared. D is the distance between two axes. This is d. In this case, d is the half of L. So d would be half of the L squared. So if I want to find the I with respect to z-axis, I'm going to add 112 ml squared, which is the mass moment of inertia with respect to center of gravity, plus m d is going to be L over 2. If I square that, 112 ml squared plus m L squared divided by 4. This is going to be 1 over 12 ml squared plus ml squared divided by 4 is going to be 3 ml squared divided by 12. 3 ml squared plus 1 ml squared is going to be 4 ml squared divided by 12. 4 divided by 12 would be 3. 1/3 of ml squared. So if you look at this, you can see why the I with respect to the new axis should be 1/3 of ml squared. We call this transfer theorem, also called the parallel axis theorem. You may need to use them. I'm just reviewing. One more thing about mass moment of inertia. If you remember, I said that if you have a mass point, the mass moment of inertia is going to be mr squared. So if I have a rigid body, and if I know the I with respect to this axis is Iz, if I know the second moment of inertia is Iz, I would like to replace this with a concentrated mass located with the mass of m, which is rotating at the distance of k from the center. So if this is the case, the I for the new system is going to be m times k squared. Now the question is, how much should be the k such that it's going to give me the same mass moment of inertia for the original system? So what I'm going to do, I'm gonna set this equal to the IZ. The mass moment of inertia for this system is IZ. I'm setting this equals to mass times K squared. And I'm solving for K. K squared would be IZ divided by M. And K would be square root of IZ divided by M. We call this K radius of gyration. You guys remember this stuff from dynamic? Sort of. So I replace, this is my original system, the original rigid body. I replace, and I know that the mass moment of inertia of that, about this axis is now IZ. I would like to replace this with a point mass, which is located at the distance of K. What should be that K to give me the same amount of mass moment of inertia? This is how I can find K. Any question so far? All right, now we are gonna start force analysis. It's gonna be line, but it's straightforward. So make sure that you're following me step by step. And if you get lost, just stop me and ask me about that. Because the homework that I'm gonna post tomorrow, it's one problem. We are gonna use everything that we have learned so far to do the force analysis of a 4-bar mechanism. So we have two-dimensional system. So we are gonna get 3 equations. One, force in X direction. Summation of the force in X direction according to the second Newton's law should be the mass of the rigid body times the acceleration of center of gravity in X direction. Center of gravity in Y direction, and summation of the torque applied to the rigid body should be equal to the I mass moment of inertia with respect to center of gravity axis multiplied by alpha, angular acceleration of rigid body. So when we want to do this force analysis, first of all, we should be done with the kinematic analysis. I mean, displacement, velocity, and acceleration should be done. If we do that, we can find alpha, we can find acceleration of center of gravity in X and acceleration of center of gravity in Y. Then we can start force analysis. At the end of this lecture, I'm gonna do the force analysis for a 4-bar mechanism, but for now, I'm gonna do only for one rigid body, which is gonna be the link 2. I'm not looking at link 3 and link 4, I'm just looking at link 2. So link 2, if this is the origin, suppose center of gravity is located here at the distance of R G2. the distance of center of gravity from the origin, the dual representing the link number. Link number 1 is ground, link number 2 is this. So this angle is theta 2. Alright, if I have a 4-bar mechanism, when it's running this mechanism, if I'm looking at the free body diagram of this rigid body, link 2. Link 2 has been connected to link 3 through this point, and it has been connected to link 1 through this point. So these 2 points are the points that the forces gonna apply to link 2. The ground is going to apply the force to link 2 through this point, and link 3 is going to apply the force to link 2 through this point. See how I'm going to use this notation. F1 to X. 1 meaning force coming from link 1, this is ground, applied to link 2 in X direction. I represent that with F1 to X. So that force has one force in Y direction. So I represent that with F1 to in Y direction. So F1 to X, F1 to Y. So at this point, which is point, for example, if this is point O, A, at point A, the force coming from link 3 is called F32 in X. F32Y. F32 meaning force coming from link 3. The first number is representing the link that force is coming from. The second number is representing the link that force is going to apply to that. So F32X meaning the force coming from link 3 applied to link 2. And this is what we are looking at in X direction and Y direction. There is external torque applied to this link. I represent that with TS because we are going to add a motor here. It's going to run the mechanism. So external force is going to be TS. Any questions so far? So now we are ready to write these 3 equations, which are the equation coming from the Newton's law for this single rigid body. So let me represent the force here, F1 to X. F1 to Y. Summation of the force in X direction, set it equals to mass of link 2 times acceleration of center of gravity in X direction. I start from left side. F1 to X is one force applied in X direction. F3 to X is going to be another force applied in it's going to be equals to m mass of 2 acceleration of center of gravity for link 2 in X direction. second equation, the only force that I have in y direction are F1 2y plus F3 2y equals to M2 acceleration of central gravity in y direction. Summation of the torque with respect to center of gravity. Left side. I have external torque coming from the motor. I assume that it's going counterclockwise, so TS is gonna be positive in the equation. What would be the other elements of the torque with respect to center of gravity?
All for F3 to F3 to F1
So exactly, this force is gonna make torque with respect to center of gravity because it has a distance in y direction with respect to center of gravity. This force is gonna make the rotation or moment about center of gravity because it has this distance in x direction from center of gravity. This force is gonna have this distance from the center of gravity, and this force is gonna have this distance from the center of gravity to make a rotation about that. So what I need to do, I need to find the moment that each forces are making about center of gravity. And I should be careful about the sign. So this force, you can imagine, this force is making counterclockwise rotation, so it should be positive. And how much would be the torque? This times this distance. This guy is RG2. This distance is going to be RG2 sine of theta 2. So F1 to x times RG2 sine of theta 2 is going to give me the torque coming from this force. Now this force times this distance is making clockwise. It's gonna rotate the center of gravity in this direction. So I put negative here. How much will be the magnitude? It's gonna be force times distance, perpendicular distance. So exactly F1 2y times RG2 cosine of theta 2. This distance from this point to this is gonna be RG2 cosine of theta 2, which is going to be this guy. Now, we should look at this force. This force is going to make a rotation in clockwise, this force. You see, it's making clockwise about center of gravity. I put negative. The magnitude of moment is going to be the force times the vertical distance. How can I find this distance? From here to here is R2. From this point to this point is R2. R2 minus RG2 is going to be from here to here. So this is going to be R2 minus RG2. So if I'm looking for this guy, it's going to be R2 minus RG2 times sine of theta 2. This angle is theta 2, same as this one. So R2 minus RG2, let me first write force. F3 2x times R2 minus RG2 sine of theta. And the last term for the moment is coming from this force. The force is making about the center of gravity, is making counterclockwise rotation in this direction. So I put positive. How much would be the moment? Force times this distance. This distance is R2 minus RG2 cosine of theta 2. So it's going to be positive F32y R2 minus RG2 cosine of theta 2. And this is going to be equals to I for center of gravity of link 2 times alpha 2. Right hand side of the equation. Question on this. What I'm expecting you to do, finding the moment that each force making about center of gravity. And the moment is going to be the force times the perpendicular distance from center of gravity. So in each case, what I did, I looked at this force. This force has this perpendicular distance. What would be this distance? Is going to be RG2 sine of theta 2. Is it making counterclockwise or clockwise? This force is making counterclockwise, so I put positive. For this, is going to be negative, and the perpendicular distance would be this, or RG2 cosine of theta. Similarly for these two forces, except the distance is going to be this times sine and cosine, and this distance is R2 minus RG2. So, and set it equals to mass moment of inertia according to times the output. Any question on this? So make sure that you know what I have done, because we are gonna go to the 4-bar mechanism shortly. You are here. We have 3 equations. Over there, we have 3 moving links times 3. We are gonna have 9 equations. Good. All right. So for this specific example, assume the value for these two forces are given. F32x and F32y are given. So if they are given, we are solving for F1 to x, F1 to y, and how much torque do we need? Let me call F32x as a FPX and FPY, just to make sure that they are good. So I'm gonna change this to the matrix form. So I'm gonna move everything which is now to one side, and all terms which they are not known in another side. But before we go through that, is this term noun or unknown? It's noun, because how can we find, let me go to that slide. This one. I'm looking for acceleration of center of gravity after I'm done with velocity, for displacement, velocity, and acceleration analysis. How can I find the acceleration of center of gravity in x direction? I should start from origin, try to get this point. X component of center of gravity would be RG2. Here we have A, right here we have RG2. I can use A just to get this equation. A cosine of theta 2. And Y of center of gravity would be A sine of theta 2. If I'm looking for displacement and velocity, I differentiate once. Negative A theta dot 2 sine of theta 2 y dot of center of gravity would be a theta dot to cosine of theta. Acceleration x double dot of center of gravity of 2. I differentiate one more time. I should differentiate the first term. A is constant, so I'll keep it there. Negative a theta double dot to sine of theta 2. Now I'm gonna differentiate this. Negative a theta dot 2 squared. If I differentiate this, theta dot 2 is coming out. Multiplied by this is gonna be squared. Cosine of theta. And y double dot of center of gravity would be a theta double dot to cosine of theta 2 minus a theta dot 2 squared sine of theta 2. And this is acceleration of center of gravity in x direction, and this is the acceleration of center of gravity in y direction. So those are now saying that I'm gonna rewrite these three equations in a matrix form. F1 to x is unknown. I'll keep it this side. F1 to x equals to mass of link 2 acceleration of center of gravity x minus fpx. Fpx is f3 to x. If I move this to the right side, it's going to be negative f3 to x or fpx. Second equation, f1 to y is going to be m2 acceleration of center of gravity in y minus fpy. And last equation, this term is noun. This term is unknown, sorry. It's unknown. F1 to x is unknown. F1 to y is unknown. But F3 to x is Fp. The other terms are given. So I'm going to move these two terms to the right hand side. On the left hand side, I'm going to get Ts plus F1 to x Rg2 sine of theta 2 minus F1 to y Rg2 cosine of theta. Yes.
Is it possible that we would know what F3 to x, the F3 to x and y, without actually knowing the input force from the motor?
We don't know. We are gonna find out.
Isn't it the one that we're supposed to know first that will allow us to find force?
In this example, the reason that I brought this example because I wanted to show you how can we set up the equation. Then I'm gonna extend it to the 4-bar mechanism. On 4-bar mechanism, we don't know F32, we don't know F32y, we don't know F12, and we don't know Ts. We are solving for all of those unknowns. Not input force, not input torque, none of them are known. It's here I'm just, since with 3 equations I can solve for 3 unknowns, I'm assuming these 3 are given. Just to show you how you can set up the equation, most likely tomorrow, we are gonna derive 9 equations and 9 unknowns. What would be 9 equations? What would be the 9 unknowns? I have 1, 2, 3, 4 joints. Each joint has 2 forces, one in x direction, one in y direction. 4 times 2, 8. And what input torque? 9. And each link is going to have its own 3 set of equations. We can solve 9 equations by 9.
So just to do the force analysis, we would have to start from the displacement, then do the velocity, and do
And the acceleration, yes.
And that gives us the acceleration, which
Yeah.
would cause the force.
And it's the reason that I like the homework 8 because it's asking you to do the force analysis and it's based on what you have done for the last 3 homeworks. Homework 9, sorry. On that homework, I'm asking you find the angle at which we need the maximum torque. Then you have to do the force analysis for all 360 degree and just look at the curve where is the input angle at which the maximum torque is needed. Or if you are looking for the maximum force applied to the link 2, you can find that angle. Okay, let's back to this example. So the left side is unknown, right hand side is gonna be positive I for central gravity of link 2 times alpha 2 plus fpx. This is fpx, negative is gonna change to positive, times R2 minus RG2 cosine of theta 2 minus FPY R2 minus RG2 sine of. FPX is sine. This is going to be cosine. This term has sine, the second term has cosine, and it's positive, so if I move it to the other side, it's going to be negative. So this is the form that I can change it to the matrix form. So I'm going to have this 3 equations, 3 unknowns. My unknowns would be f1 to x, f1 to y, and ts. f1 to x, f1 to y, and ts. I start from first equation. What would be the coefficient of f1 to x? It's 1. So the first cell is going to be 1. First cell corresponding to first step. And the first equation, the coefficient of f1 to y is 0. We don't have any f1 to y. And we don't have ts. Right hand side, we have m2, acceleration of center of gravity x, minus fpx. Second equation, the coefficient of f1 to x is 0, coefficient of f1 to y is 1, and there is no ts. There is no torque showing up on that equation. And this is going to be m2, acceleration of center of gravity in y, minus fpy. And last equation. If you look at the last equation, the first term, the coefficient of f1 to x is this guy. Coefficient of f1 to y is negative RG2 cosine of theta 2. Let me plug in there. R2 minus RG2 times sine of theta 2. Second term is negative R2 minus RG2 cosine of theta 2. And coefficient of TS is 1. TS has the coefficient of 1, and right hand side is going to be I2 times alpha 2 plus the rest. This term and this term. FPX R2 minus RG2 sine of theta 2 minus FPY R2 minus RG2 cosine. Plug in the numbers here. Theta 2 is given, R2 is given, location of center of gravity is given. So this metric is given. Acceleration of center of gravity for link 2, I already showed you how you can find that. Mass is given. Fpx, I assume it's given for now. So this term, and this term are given. So it's A times X equals to B. Use the MATLAB A/B for your matrix, your calculator to solve for this problem. How was that? It's a line, but it's a straightforward. So if you got confused, that's okay. You can just look at the notes again, and if you have any question, we can discuss. Which term? That's last row. F. Last term you mean? Yes, S theta 2. I didn't have space, so I just showed. S meaning sine, C meaning cosine. So let me, yes.
Why do we have this here? Shouldn't it be R2 sine, not R2 minus R2?
R2 minus R2. What should we have here?
I mean, for F1 to X. From the equation?
This guy?
Yes.
Okay, what should
It should be R2 sine minus, not the negative.
Yes, thanks for catching. It should be R2. And this should be negative RG2, sorry. Revise that. Then here, the coefficient of F1 to X is RG2, not R2 minus RG2. Alright, let me any question on this? So I'm going to solve one example on this, and then we are going to move to the 4-bar mechanism to set up the system of operation, and we are going to do that tomorrow. And after tomorrow, we can start kinematic synthesis next week.
So the next test you have all of this.
And the next exam is going to cover velocity, acceleration, force analysis, and partial parts of kinematics. The final exam is a comprehensive, so you have to practice. Any question on this?
The alpha 2 is just theta 2 double dot.
Yes, alpha 2 is the angular acceleration. It's given it's an input that you have to provide. When we did the velocity, when we did the acceleration analysis, input angle, angular velocity of input link, and angular acceleration of the input link were given.
And it's almost always a constant.
If the motor is running at the constant speed, alpha 2 is going to be 0.
Yes, but like alpha 2 is always like a number. And
Yes,
the other ones with
yes. It's a scalar. Any other question? All right, we continue tomorrow.